Okay, so I hope the screen is visible, right?
Yes, ma'am.
Yes, yes, okay. Fine. So, what were we doing last? It feels like eternity since we met because yesterday we didn't meet, so it feels like a long time. Anyway, we were looking at these informed search methods, right? And we in the very beginning we started off with uninformed search, and we kind of figured out that there's a lot of exploration being done in uninformed search, especially uniform cause search was the best in that space, and there was a lot of exploration being done. So that's when we thought, okay, if we have some more information about the problem, the search problem, and how far we are from the goal state at any particular state, then maybe we can reduce the time spent in exploring unnecessary states. And that's when we went to informed search. And here we started off with the most naive method, which we called as the greedy best first search. So it was the same algorithm as uniform cause search, but you exclusively what you push into the queue is the heuristic. Okay, so here is where we started looking at heuristics, which tell you how far it gives an estimate of how far you are from the goal state. Okay, and that was with greedy, but there were some issues. You were not always guaranteed to get the optimal, even for this example also. Okay, so that's when we kind of wanted some good properties of both UCS and greedy. So we wanted something which didn't do much exploration, but was still optimal, and that's where we started looking at the A star algorithm. So here the priority was just a modification. So it was the sum of what this g of n. So the total cost up to a node n. So n is some state. So the priority function is given by the total value of the cost all the way from the start to that node. So that is g of n. And if you have started reading the textbook, you would also know seen some other names given for these terms. So g of n is usually called the backward cost. Okay, so that is the cost all the way from the start to a particular node. So if you want to find g of a, this node a, for instance, then it's leaving behind how much cost have you already traversed. That is g of a, and you have h of n, which is a heuristic which tells you how far a is from the goal. Okay, so h of n is also called the forward cost. Okay, so how much more do you have to travel? And this is a heuristic. So many times you don't know. Mostly you don't know. The exactly how much is going to be the cost unless you have actually traversed that path. You don't know. But this is just an estimate. So essentially, what A star is doing is it wants to take the overall cost of a plan. Okay, so if you're going to take this plan SAG, it actually wants to find the overall length of this plan, right? But it knows, like till A, it knows for sure what's the actual cost, but further ahead from A, it doesn't know. So that's why it uses some estimate for the remaining part. Okay, so now if the h of n, so that's a heuristic, and suppose you knew the true cost, right, from any state to the goal. If you know exactly how much cost is going to be, then what's going to happen? Do you think it will be optimal? Is it going to be optimal or no? Okay, am I audible?
Ma'am, I think your voice broke in between. Could you repeat once?
Oh, okay. So, okay, so did you hear like till the part where I mentioned what these G and H are,
Yes,
the
yes, ma'am.
backward?
Only the
Okay.
last 1 minute, I think.
Okay. So what I'm asking is, essentially, A star is trying to give you, use the total cost of a plan, right? It's trying to find g of n plus h of n. So gn is the cost till you reach a node n, and h of n is the remaining cost. It's an estimate of the remaining cost. So suppose instead you had, h star of n, which we defined as the true value of the cost from a node n to the goal. Okay, so instead, suppose you use g of n plus h star n as the heuristic, as the priority, right? So in that case, are you going to be optimal? Will A star give you an optimal plan? That's the question. Right. So, what do you think? Is the question clear? What I'm talking of?
Yes, ma'am. I think it
Yes.
should give the optimal value because we know the previous and forward path, what cost it has.
Yes, exactly. So this is exactly what we mean in terms of optimal, right? Like we want this, the plan that minimizes this. That's what we call as the optimal plan. So if you use the true distance, of course it's going to be optimal. And if you already knew it in the first step itself, in one shot you're going to directly get the plan, right? I mean, you're not going to do any exploration. You will directly get the best plan. You'll start with, if so here it's as if saying h is 3. Okay, so suppose here h, so another heuristic is h2 is equal to 3, which is the exact cost, and h2 equal to 2. So now if you use h2 instead, what's going to happen? So in the first time itself you're going to get it, right? So for a, the total value of the heuristic, I mean total value of f would be 2 plus h2, so 2 plus 2, so 4. And for b you're going to get 2 plus 3, which is 5. Okay, so already you have detected that A is the best way to go, and from A you will eventually hit the goal. So you won't even explore B. Okay, so if you knew exactly in one shot you're going to get the optimal, okay, without any exploration, but you don't know the true cost. So that's where you go for heuristics. Okay, and we kind of worked out this example with assuming the heuristic values of this h. Okay, and we traced this. And for the Pac-Man example, we looked at some examples of heuristics that you could use. One was a Manhattan, and the other is Euclidean distance. That's also a possibility. But you have to use what makes sense for the application. So these heuristics are mostly determined by the application. And then we were also looking at this example where if you choose a wrong heuristic, the heuristic has to satisfy some properties. If it doesn't, then you can end up not being optimal. So one example was this case where for node A you have h equals 6, whereas the true cost of getting from A to the goal was just 3. Okay, so here the issue is, I mean, whatever it returns is going to be not optimal, right? Because the issue is that this heuristic at any node is, it's above the actual cost. So you don't want that. So that's where we define what was called admissible heuristics. So at every node, you want the heuristic value to be giving you a value less than h star, which is the true cost from n to a goal. Okay, so this should happen for every state n. So this is a desirable property. Now, we also saw another example. This is where we kind of stopped, where we have an admissible heuristic here, but when you trace the A star algorithm, what happens is, for this example, the shortest path here is along the, what's the shortest path? It's SACG, right? So a total cost of 5 from SACG, but whereas A star is going to go along this path, SBCG, so which has a cost of 6. Because the reason is that it first travels along B because the heuristic said it's 1, and the total cost, I mean the total F value is 2. It expands along this this path. Okay, and it reaches C, it marks it as visited, so there's no chance to revise to a different path. Okay, so here the issue was again with the heuristic, and what happened was this issue, right? So from A to C to G there's a path, and according to the heuristic value, from C to G the heuristic says the cost is 1. The actual cost from going from A to C is 1. But the heuristic is saying that the cost of going from A to G is 4. Okay. That's what in some sense it means when you say H is 4. It's as though it's as though your heuristic is saying that the cost of getting to G from A is 4. But here you see that there is a shorter cost if you go from A to C and C to G. As per the heuristic itself, it's not consistent, right? So that's this is the issue with this heuristic. So what you want is consistency. So I'll just write here. So in this example, consistency doesn't hold. Okay, so let's just formally define what it means by consistency. So consistency is something like the triangle inequality that you have seen earlier. So if you have a node A and there is a state B here and you're getting to the goal. So there are these two paths, right? As per the heuristic has to be consistent with itself. That's where the name consistency comes. So there is a true cost here. So this is the cost from going from A to B. I'll just write it in this way: C actual cost of going from A to B. And here there is a heuristic. So H of B is what the heuristic tells you, and there is also an H of A. So what consistency says is that you always should have H of A should be less than the cost of going from A to B. So this is the true cost plus H of B. Okay, it can never exceed this value because if you have to get from A to G, then this is also one candidate path from B to G. So the actual heuristic cost should not exceed the cost of going from B and going via B. Okay, so this is the true cost. So this is what consistency means, and this should be true for every state A, for every state. So for every state A, and for all successors, right? All successor states B. Okay, this has to be this has to hold true, and that's when you say that the heuristic is consistent. Okay, so one thing is that maybe this is something that you should try to see. So the two properties, right? Admissible and consistency. So one thing is that if a heuristic is consistent, it will also be admissible. Okay, so this you should try to see why this is true. So I will leave this as an exercise for you. So it's not too hard. It's just you can just use these properties, the definitions. With the definitions, you should be able to get it. So this is always guaranteed. So in that sense, consistency is a stronger property. Okay. Now the result in A star is that if the heuristic is consistent, then A star is going to be optimal. So let me just write the statement. So if heuristic is consistent, then A star in the way we have defined it. So A star. So this is actually what we have shown is a graph search algorithm, right? Because we are keeping track of the visited nodes and we are proceeding that way. It's not like we are assuming that you enumerate the search trees. We are not doing it on the tree, we are doing it on the graph instead. So if the heuristic is consistent, then A star is guaranteed to be optimal. Guaranteed to be optimal. Okay. So I will just prove this in class today. But are there any questions so far on consistency? Is this notion of consistency clear? Oops.
Yes, ma'am.
Yes. No? Yes. Okay. Yes. Okay. Can I also hear from some of the others? You can type or you can say. Yes. All right. Okay, so I think a good number of you is convinced about this. So I will prove this. Now, one thing I want to say here is in the standard proofs, there is a subtle issue. Okay, and this is something I discovered yesterday. I mean, all this while I was going through, and I thought it's fine, it makes sense. But yesterday I discovered there is some issue. So I will anyway tell you the proof. You tell me if you find some issues, okay, or if it looks fine, maybe it's fine, okay. So keep, watch out very carefully. So let's see why this is true. Okay. So the first claim is to say that, along any any path you take. Okay. So this is a graph, and you're going all the way till you find a goal node. Okay. And suppose you're starting from some state n, and there is this entire path that is traversed, right? And so maybe you have an n1, n2, and so on till you finally hit the goal. Okay. Now there's an alternate way also, perhaps maybe from n. I mean, there is some part of the graph here, but you know you there are different goal states, and an intermediate stage is the state n, and perhaps another path is, maybe you go along another set of states. Okay, so maybe let me call it A1, A2, and so on. Okay, so these are the set of other possible states which will culminate at a goal node. But this is say it's a bad goal node. So this is a bad goal state. Okay, in the sense that it is a suboptimal way to get there. It's a suboptimal goal state, and this is the best goal state that you want to reach. Okay. So G is the best goal state and B is the bad goal state in terms of optimality. Okay, so the claim is that always A star is going to hit G. Okay, if the heuristic you have is consistent. So the first way to the way to approach this is, first you see that along any path you take, okay, the value of the f, so f of any state is this G plus H. Okay, and this heuristic is consistent. So the these f values are going to increase along every state. So along every state in a path, um, along every state in a path, the f is non-decreasing. Okay, or it's, yeah, so it's non-decreasing. So this is the first claim. So we will come to this now. I will tell you why this is true. So if this is true, now the next idea is that, so you have these two states, right? I mean, these two paths, right? From somewhere, like you start from some S, and you branch out, and something like this happens. Okay, so the idea is, like, suppose n is on your priority queue, then what you have is f of n is going to be less than f of n1, and so on up to f of whatever this is. So this is, maybe let me call it np, and then you have the goal state. Okay, so this is from the first property. This is true. And also, if you apply the same thing for this other path, right, you'll get f of n is less than f of a1 and less than f of a2, and so on up to f of, let me just call it something else, maybe am, maybe, because there are m nodes here. So this last one is am, and this is also in turn less than f of b. Okay, so that's what the first one gives you, the first statement gives you, which we will prove. Okay, the first statement we'll prove later. But if you assume that the first statement is true, then this is true, right? You just apply this to every path. Now what you have is, let's just look at f of g and f of b. So f of g is the value of g plus h of g. Okay. So G is a goal state, so H of G is always going to be 0. Okay. And now for F of B, again you have G of B plus H of B, right? So what is the value of H of B? H of B is how far you are from B to any goal state, right? It's a heuristic, so remember it's consistent. So what should it be? Can somebody tell me what h of b is going to be? What do you think?
B is also the goal state, right?
Yes, b is also a goal state.
So it should be 0.
Zero, yeah.
It is 0, right? Okay, so the only thing is it's a bad goal state, it's a suboptimal goal state. So what it means is that g of b, that is the true cost of going from the start to the bad goal state, so that is larger than, strictly larger than g of capital G, okay? Because b is suboptimal.
But we have to prove this, right?
No, this is given to you. Okay, g
Okay,
of
okay.
b. It's you assume that there is a bad goal state and a good goal state. Okay, so this is known. Okay, what you have to show is that you will always reach g first. If you apply a star, you will pop out g first before you pop out b. Okay, so so what this is telling you is now f of b is just g of b, and f of g is just g of g. And what this in turn gives you is f of g is going to be, okay, let me write it as f of b itself. F of b is greater than f of g. Okay, so partly it's this is what you want. The heuristic f is going to be worse off for the bad goal state than for the good goal state, so that is a nice thing. But all you want to now see is that this is true, but it shouldn't be the case that you end up not pushing g into the queue before. So when will you identify b? I mean, when will you detect b? When will you reach b before you reach g? That will happen. That can happen if in your queue this g is not there, but somehow b has come in, and so even before you push g into the queue, there is this b which you find and you pop it out, and then you finally conclude that you have reached a goal. So the thing is that you have to show that this will not happen. So partly this helps. Now yeah, so now for the remaining part, to see whether can you end up visiting all this path before the n1 path, n1 n2, before visiting that path, can you end up traversing the a paths? Okay, so that's where this statement helps. So you are at some ancestor n. Okay, and there are these possibilities that you could go to. You could either have gone through n path, this n1 you could have pushed, or a1 you could have pushed. So maybe if you choose something like, okay, maybe a1 is a lower value in terms of f. Okay, suppose that is the case, and you end up going along this path. Okay, now since you had n1, you would have pushed both these. I mean, since you were at n at some point, you would have pushed n1 as well as a1 into the queue. So both these would have been in your queue. So this would have been in your queue, and this would have been in your queue. Okay, and somehow because a1 maybe had a lower f value, so you started going along this path. You started going all the way till here, and you reached till b. Okay, now till am you went along, because suppose all of them were less than f of n1. Okay, but what's going to happen at this point is that let's see what happens between f of n1 and f of b, right? What Okay, so let's just look at these two. So maybe let me just write this on a new page so that it's okay. I'll write it here. So this was the relation we had, right? And yeah, you've gone all the way till here. These have all been traversed, and now you have n1 is on the queue, and you have f of b. Okay, so now which is lesser? Is it n1 or is it b in terms of the f values?
And FP is
N1.
lesser than FN.
N1,
Pardon?
N1 will be lowest, right?
Yes, n1 has to be lowest. Why?
Because
Because
FB is
N1
greater
is
than
less than
FG
G.
and Yeah, N1 is less than Fg.
So Fn1 is less than Fg, and we just showed that Fg is less than Fb, right? So out of these two, at some point you will end up, popping out N1, and then you will switch to this path, and finally you will reach the goal. Okay, so so that's the idea of this proof. Now what remains is to show that, this step, this one we didn't show. So along every state in the path, f is a non-decreasing, or it's at least, the same value, or it increases as you go along. So let's try to see that. So okay, so let me just write it again. So you have n1, and so on, and up to you reach some goal. Okay, so the claim is that claim is f of n is less than or equal to f of n1 for any path. So for any n and n1 on a plan. Okay, so let's write what f of n1 is for this. So f of n1 is g of n1 plus h of n1. Okay. Now, what was g of n1? This was computed like from g of n plus this cost, right? So this is c of n to n1. This is the true cost. Okay, so this is exactly c of n, g of n plus c n to n1 plus h of n1. Okay, is this okay?
Yes, ma'am.
Yes. Okay. So now is where you will use consistency, right? So C of n to n1 plus h of n1. This quantity is greater than h of n. Okay. So if you remember, that's what we defined consistency as, right? So okay, let me write it here itself. So yeah, h of n is this what you have at this state, and that is going to be less than this cost, the true cost of getting to n1 plus the heuristic value. So that's just consistency. So overall this is greater than g of n plus h of n, which is just f of n, right? So yeah, this shows that, f of n is less than or equal to f of n always, right? So this completes the proof, right? Any questions on this proof? Does it make sense?
Yes, ma'am.
Yes, ma'am.
Yes?
Yes, ma'am.
Okay. I also want to hear from some of the others, maybe Jaishika?
Yes, ma'am.
Yes? Okay. So this is where I have some issues with this proof. I mean, there's some subtleties which I feel is not fully, it's not very satisfactory for me. Okay, and that is in this part. Okay, to show when you claim that f of n is less than or equal to f of n1 along every, path. So the issue that I find is a little unsatisfactory is this step, right? G of n1, to say that it's equal to g of n plus this cost. Okay. Uh, the issue is, you can have some other path, right, which comes this way, and that could have a lower g value, right? This is okay. This is if you take just this one path, yeah, it's true. But if you had multiple entries into n1, then the g values of that n1, if you look at it as a shortest path from the start, then there is an issue, right? Like maybe let's just see one example. Like I was, which I just thought of yesterday. So yeah, just correct me, okay, if there's something. I mean, I think the proof is like, okay, the statement is right that if it's consistent, then you are guaranteed to be optimal. But it's just that the proof, there is some subtlety which it has to be made a little more precise. Okay, so the example is this. So suppose I have a start state here, and I have a. This is a, and there is an n. There is an n dash. Let me write it a little big. So n dash, and then you have the goal. Okay, and there is another path, maybe B, and B is coming to N dash, and the costs are like this. You have 2, 2, 2, and maybe this is 8, and then you have a 3 here and a 2. Okay. Let me also write the heuristics. So we want a consistent heuristic. Let's just exactly take this distance itself. So for here, h is 8, and in this case, h is 11. So it's 8 plus 3, 11. And here you have h is 10, h is 12. Okay, and start state, okay, the NV doesn't matter. So we can just keep it as h is 13. So it doesn't really matter. Okay, so in this example, what's going to happen? Let's just compute the f and g values, right? So here you're going to have g is what? It's just, what is the value of g here for this node B?
2.
2. And for A,
2.
2.
2. 2. So now you have, so f of A is going to be what? So what
13.
is f? So f of A is 14,
14.
right? 2 plus 12, 14. Now f of
So,
B is what? Somebody had a
13.
question?
13.
13. Okay, so now let's come to n. So n had a, what is the value of g here?
4.
4. So you will have f of n is what? 14.
14.
14.
14, right? Now let's come to n dash. So n dash you would have come from this path, right? Like if you trace the A star algorithm, what you would do is you will push B, and because this out of A and B, this was the lower value, and then you would come to n dash, right? So here, what is g of n dash going to be?
5.
5.
5.
5. So f of n dash is going to be
13.
13. 13, right? Okay, and for the goal state, what is it going to be? You will trace along this path, and finally the goal state has g of g is equal to
13.
13.
13, right? And so f of the goal state is 13, right? So here h is 0 anyway. Okay, so the algorithm works, but if you look at this path, right, if you take a path along this path, like if you take S A N N dash G, so the f values for let's start with A. So you had 14 here, for N you had 14, and N dash is 13, right? And 13. Okay, so there is an issue here. It's not going to increase throughout, right? In this path, if you take, you're not going to get the f values as increase. I mean, it won't increase, right? Do you see the issue?
but why are we taking the path like that? Like, why are we going to state A from state S?
Yeah.
Because
So, yeah.
like
Can you say?
f of B is like less than f of A, then we should follow the path through B.
Yeah, so this is the thing, right? Like, I mean, it's not true to say that, for every path, if you take any, path, you're not going to have this, right? It's something you have to make it a little more precise, that it's the path traversed by A star, or, the optimal path is going to have this. And you need to have some more argument to say that, it is going to go along the optimal path only. It's not going to take any other path, right? It's not going to switch. So that is something you have to state. It's not true to say that for any path or any plan from the start to the end you're going to have this. That's not going to be true. Okay, like that's one thing which I see in textbooks. They don't make this very clear, and even many other resources also. Even the Berkeley resource, I don't see this being explicitly stated. Maybe it's something which is implicitly there, but you have to state it clearly. Okay, so you get the issue, guys. Is the problem clear? Like what I'm saying, what the subtlety is?
Ma'am, I think if we take that part, then fn dash will be 14 only because the sorted path will not be calculated then.
Where? Which one? For
If we take like that A1A part, then I think the
Mhm.
fn dash will be 14 only.
So if you traversed along this path, I mean,
Yes, ma'am,
suppose you didn't have this path.
yes, ma'am, because if we don't go through B, then fn dash
Mhm.
will not be calculated as from that value. So it will be 14, 14, 14, 14.
So suppose you didn't have this path via B, then it's
Yes, ma'am.
fine, right? Then you are going to have, so suppose B was not there, you will have, even for n dash, you're going to get G will be 6, right? 6 plus 8, 14 you will get, right? That is fine. Like if this was the only path, S, A, N dash G, then it's fine. You're going to get, you're going to get this property. But the moment you have something like this, it's along the path that A star traverses, it's fine. I mean, then it's still okay, right? But it's not right to say that along every path in the graph or along every path in the search problem you're going to have a non-decreasing property. That's not true, right? Right, Himanshu,
Yes, ma'am.
does it make sense?
Yes, ma'am.
Yeah. So I mean, I just want to point to this this subtlety here. So when I mean, you can try to see if adding necessary qualifiers will complete the proof. And I'm not going to quiz you on this, okay? But this is just to say that there are sometimes these issues are there, so you have to keep an open mind when you read the textbooks, and don't believe everything just because it's there in the textbook. You have to think through it on your own. And sometimes people make mistakes, or sometimes people think in some way, but when they write it, they might not make some things very clear. Okay, so as students, as people who are working in this field, you have to be wary of that fact. Okay, and you have to think
Ma'am,
through things yourself. Yeah.
okay, ma'am, I think like the most optimal path, this issue will not be there. Like for the
For
optimal path.
Yes, I agree with that. So if you take the optimal path, then you're guaranteed that this property will be true.
Yes, ma'am.
uh, s- right, so that we can see that. So now the thing is to just say that you will take the optimal path only. It will not go into some other path in between,
Yes, ma'am.
right? So that also some additional step is needed there, right?
Right, ma'am.
Yeah. Okay, so yeah, this is about the optimality of this algorithm. So let me know, okay, if when you try this on your own, if you have some ways in which you can complete it. I mean, what Sahil said was right. So if you formally are able to write it down and complete the proof, please let me know. Okay, so this is something I just discovered yesterday. When I was just glancing through to see what I want to do today. Like, I mean, this was something I wanted to do last week itself, but yesterday again, when I was just brushing through, I discovered this issue. So, and you just let me know. Okay, so now, so let's take in faith that if it is consistent, if the heuristic is consistent, you are going to be optimal. So I don't have doubts that the theorem is wrong. I think that is right. It's just the proof has to be resolved. Now, one other thing is, a distinction from this tree search. Okay, so if you remember in the last class, I was telling you that there's some things people call as graph search. Like what we are doing is a graph search. And sometimes what people do is they enumerate the tree, that you construct the search tree and run your algorithm on the search tree. So so there you don't miss, I mean, the way the search tree algorithm goes is you don't keep track of the visited nodes because you're explicitly enumerating every plan. Okay, but yeah, so there are these issues like if the tree becomes infinite, then there is a problem, but otherwise it's okay. Okay, so now it turns out that if you're doing a tree search version, then admissibility is actually enough. Okay, you don't need consistency. This consistency is mainly coming because of you're keeping track of the visited nodes. If you remember, that's how we motivated it, right? Even in this example, the issue came because you visited C first, and there was no way to backtrack and find this other solution. So that's why you needed consistency. But instead, if you had the search tree for this problem, so the search tree would be something like this. So let me just write it here itself. Okay. Okay, I'll just write it a bit small. So the search tree would be something like this, right? So you start with S, you have an A, and you have a B. Then from B, you have a C, and you have a G. Okay, and from A, again, you have a C, and you have a G. You can do the same algorithm, assuming that your graph is now this tree. Okay, so there is a replication here. Things are repeated, the states, but you consider them as different states. Okay, so try to do A star for this, for the search tree, assuming the search tree is your graph with, with this heuristic. So this heuristic that I gave here is admissible, but it's not consistent. So try this and see what happens. Okay, so this is a homework. So try A star with on the search tree. Okay, and the heuristic is just this one, the same heuristic, which is admissible but not consistent. So you should see that you will get the right path there. Okay, so that's something to note. So many times, if you're going to do a search tree kind of implementation, then it's enough to have admissible heuristics, but otherwise you should have consistent heuristics. Now for the lab exercises, there'll be some parts in the later questions where you will have to design heuristics. So there you're going to do a graph search version, so you have to ensure that your heuristic is consistent. Okay, now on the choice of heuristics, right? What is the best heuristic? Like for a problem, you can have different kinds of heuristics. Now, how do you choose one of them, right? So for this, I just want to talk of this example called the 8 puzzle problem. Okay, so you might have seen this if you have started going through the textbook or even the Berkeley lectures, they do talk of it. So let me just, these are the slides of the Berkeley lectures. So here the puzzle is just this, okay? So there are these numbers, it's a 3x3 grid. Okay, and there are these numbers, the numbers are from 1 to 8, and there is a blank tile. Okay, now what you want to get to is this last state, this one. Okay, so I hope is the cursor visible to you?
Yes, ma'am.
Yeah, cool. So you want to get to this goal state. So this is where numbers are, kind of contiguous. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what is the sequence of actions to take? So what you can do is you can move any of these tiles, like you can move up or down. Okay, so you can move this 5 to this blank. Okay, but you cannot move 7 in place of 5. You cannot swap tiles. You can move 5 to this blank, or you can move 2 to the blank. So anything can be moved to the blank, but not the diagonal. So 4 you cannot move to the blank tile, for example. You can either move 2, 5, 6, or 3 to the blank tile. Okay, so that is the way in which you do. So you see, so okay, so this intermediate action, this is something else, it's not from this state. So one possibility here is, let me just write it here, so 7, 2, 4, what's the other thing, 5, 6, 8, 3, 1. Okay, so you have 5, 6, 8, 3, 1, right? So if this is the position, now one possibility is if you move 6 to the blank, what you're going to get is 5, 6, and the blank comes here, and 8, 3, 1. So this is a valid move. So like this, there are 4 valid moves now when the blank tile is in the middle. Okay, so if the blank tile was now in this position, there are only 3 possibilities. So either you can move 6 back here, or you can move 4 here and the blank tile moves up, or you can move 1 here and the blank tile moves down. Okay, so these are the rules of the game. Okay, and the task for search problem is go from the start state and what are the sequence of moves to finally get to the goal. Okay, so is the problem clear?
Yes, ma'am.
Yes. Okay, so now here you could try to think of how you represent the states, the actions, and all these questions, right? All this, how many successors, what are the costs, all these things. This is something for you to think of. But now I'm just going to talk of the heuristics in this case. Okay, so now one possibility here is to have the heuristic. Remember, like if I'm going to capture like what if the states are going to capture the configurations, essentially that's what it's going to be. So the heuristic is telling you how far each state is from the goal, right? So one possible heuristic is the number of tiles that you misplace, because to get to this part, at least you have to move the misplaced tiles once, right? So that's why this is a possible heuristic. Okay, so at least that many actions will be there. It could be even more. Okay, so in that sense it's admissible. Okay, and right, so I hope this heuristic is clear to you. Right, so this is one possibility. So let me know if there are any questions on the heuristic. Right, I'll just maybe take about 2-3 minutes more before we wind up. Okay, so one possible heuristic is just how many tiles are misplaced as compared to the goal state. Okay, and then so here you have some kind of statistics on when you run these search problems, when you do A star, and versus when you do this uniform cost search. How many nodes do you end up expanding? Okay, so tiles is with this heuristic. Okay, and you have some number here. Now, an alternate heuristic that you can use would be, so something like the Manhattan distance. So remember that, I told you you cannot move diagonally, right? You cannot move 7 to the blank tile. So always the actions are, you have to go left and up or right and up. You have to move along the x-axis and the y-axis in different moves. You cannot make a move of both the x and the y coordinates in the same action. Okay, so in that sense, the Manhattan distance, which we saw last time, it's this, how far you go along the x to how far you go along the y. Okay, plus both these things. So that is a valid heuristic to use. Okay, so both these, there are 2 heuristics now we have talked here. So what is the right heuristic to use? How do you make a choice between these 2? Okay, so there is also a systematic way you could do this, and so that's what we will do in maybe tomorrow's class, because I think we're running out of time now. Okay, so I will stop here for today, and maybe if there are any questions, I'll hang back. Otherwise, see you all tomorrow.